this quarter, recording our classes. And I'll post these on YouTube, and there'll be a link to the channel on Canvas. Don't take this as an excuse to skip class and sleep in and then watch the video later. It's not the same, okay? This is a very interactive process of learning this material. It's going to take a lot of back and forth. There's going to be a lot of question and answer going on, and if you're not here present during class, right, you miss out on that opportunity. You can listen to other people ask questions or answer questions, but it's really, this is a subject you learn by doing. Okay, you can read the material, you can read the book, you can memorize it, you can understand every worked out example and still not be able to do it on your own. So the more you engage, the more you actually do this stuff, the better you'll be at it. And it'll help with all your courses down the road, whether you're engineering, computer science, it'll all build on top of this. So the textbook is available on Canvas through the syllabus. It's a free download. I think the bookstore also has print copies, but if you can read a PDF, you can get it from there. We'll follow the textbook fairly closely, but we won't necessarily do everything from every chapter. We probably won't do much from chapter 6. And we'll add some things towards the end that you won't necessarily find in the text. All right, I'll let you read the course outcomes. These are the things that you're hoping to leave the course being able to do. That's sort of the guaranteed part. Very, very tentative course outline. It's a 10-week quarter. This is just sort of my initial day 0 idea of how I want to break things up. We'll probably go off script pretty quickly, but that's the set of things I hope to get through, just sort of a smattering of them. There's a lot of details mixed in there. Let's talk about grades. So there's 8 labs in this course. Okay, total for labs is 25% of your grade. There'll definitely be homework. There may be some in-class quizzes. We're going to have to talk about that. But combination of homeworks and quizzes will be 20%. Midterm 25, final 30. Pretty straightforward grading system. Add them up, find the average, and that gives you a letter grade. All right, course policies. This is fairly boilerplate, but I want to hit a few things on here in particular. So academic honesty and plagiarism. It's very rare that I encounter a situation where students are outright plagiarizing, where they're saying, hey, I don't feel like doing the work, I'm going to copy someone else's work. But it's not uncommon to find people who think they're doing their work, but are actually turning in someone else's work. And it's a tricky area because we're working in groups, we're doing labs with lab partners. Hopefully people are talking to one another outside class. You might be working on homework in a study session with some friends and stuff. That's all good, that's helpful, that's important. And it models what happens when you get outside of the academic world and you're working in a job. Nobody says, lock yourself in that room, solve the problem, don't talk to anybody. Okay, that's not how things work. It's normally do whatever you need to do the best job possible. But if you're working on homework with someone and you don't understand how to do this type of problem and you say, hey, what did you do for this? And your friend says, oh, I did this kind of thing. Okay, and then you get to the next problem. It's like, I don't know how to do this. And you look at your friend and she says, okay, this is what I did. And you say, okay, thanks. And you do that all the way through the homework. You get to the end. You've never actually solved the problem yourself. But what you turned in is going to look a lot like what your friend turned in. And if I notice that, or if I see a disconnect between what you did there and what you did on the test, then it starts calling things into question, right? So the important point here is you want to make sure that you're actually getting the solutions to your problems, homework and labs and certainly exams from inside, right? That you're not seeing somebody else do it and say, okay, I understand that, so I'll write that down. So that's the more important part about academic honesty. Late papers and assignments, I'm not going to take any late work except for labs. Okay, and we'll talk about that in a minute. There'll be a penalty for late labs, but you have to do all the labs to pass the course. But everything else has to be done by the deadline. don't hack the computers too badly. That's the misuse policy. Accommodations. So Clark College is committed very strongly to making sure that everybody taking classes here has an equal opportunity to learn and to demonstrate their learning and to excel and to move on from Clark to wherever they're going next. And this is independent of whatever your particular situation may be. So if you have situations that put you at a disadvantage, right? If you have difficulty seeing what's on the screen, if you know, you have other types of issues that would be potentially interfering with your success here, there's ways to address that. So the Disability Support Services Office, DSS, specializes in working with each student to do whatever we can to help accommodate each student to be successful. So if you feel like you know, there's a testing issue, you would benefit from a low distraction testing environment, you need a note taker, things like that, come and talk to me and or talk to the DSS office. Okay, and there's a lot of resources available, and I strongly encourage people to take advantage of those. Because let's face it, college is hard enough, right? When I went to school, I was very, very lucky. All I was doing was going to school. I was a full-time student. I didn't have to worry about working. I wasn't raising a family, and it was hard, right? So most people that I encounter now, they're doing a whole lot more than just school. They're working, they're taking care of other people, and, right, so take every advantage that you can, basically. So just be aware that's a set of options available. I don't do PowerPoint, and along with that, I don't read from slides as a general rule, but I want to read this non-discrimination policy aloud because I think it's really important, and it's getting more important in some ways. So this is Clark College's non-discrimination policy, and you've probably heard this in other classes, but I'm going to repeat it anyway. So Clark College affirms a commitment to freedom from discrimination for all members of the college community. The college expressly prohibits discrimination against any person on the basis of race, color, national origin, disabled veteran status, sex, sexual orientation, age, gender identity, creed, gender expression, Vietnam era veteran status, religion, marital status, and presence of physical, sensory, or mental disability. It shouldn't need to be that long, right? We should just be able to say anybody and on the basis of anything. But we keep adding to this because that's what people do. The responsibility for and the protection of this commitment extends to everybody. Students, faculty, administration, staff, contractors, those who develop or participate in college programs. It encompasses every aspect of employment and every student and community activity. Pretty straightforward, right? So I've been teaching at Clark about 8 years. I've only had one case where this ever came up in a classroom, and it was very easy to deal with. But this does happen. And if you find a situation in this class or in any of your classes or outside of classes where you feel like there's a discrimination situation going on, please talk to somebody about it, okay? If you're in another class, you can talk to your teacher about it. If for some reason you don't want to talk to that teacher about it, you can come and talk to me about it, even if it's not this class, okay? And anyone who you talk to should be able to help you figure out what the next steps are. And in the one case where this came up in the classroom, right, basically I put this person in contact with somebody who deals with Title IX issues, and they were able to talk, and you can do a number of things in response to this, right? This person didn't want to call out a classmate, and et cetera, and so on, and so it was handled differently. But again, we're basically trying to make sure that everybody has an equal opportunity in the classroom. And if you're sitting in class and you're feeling uncomfortable or you're worried about something that happened previously or something that might happen in the future, and it's distracting you, right, that's taking away from your ability to, in this case, learn digital logic. and we don't want that to happen. So if you feel like there's an issue, even if you're not sure, if you just kind of feel like something's distracting, bothering you, whatever, right, you can always come and talk to me, and we can have a conversation about it and decide where to go from there. Code of Student Conduct, I put a link in there. You can follow that through if you haven't already read it. Class cancellations are posted on the website. Hopefully we're done with snow for spring, but you never know what could happen. And then course policies for engineering and computer science. So any questions, concerns with any of that so far? All right, let me show you some of these other details. So this is the information particular to this section of Engineering 250. So there's my office. There's a link to the online list of office hours. That's hours for myself and Izad and the other engineering teachers as well. All right, homework. So I'm trying something different this time. Normally there's a link on Canvas to the homework questions, and the homework questions come in pairs. There's a solved problem and an unsolved problem. And the solved problem shows you how to do product of sums minimization on an equation, for example. And then there's an unsolved problem of the same type that gives you a chance to apply your understanding. And I don't think that works very well for self-assessing, because you can look at the solution to a problem and modify that solution to solve a similar problem without really understanding what you're doing. Okay, it's more of a mimicking kind of behavior. And so you do the homework and you get a good grade on it, and then you get to the midterm and you get a terrible grade because you never actually learned the concepts. So I'm not going to use those problems for your homework. Now there's still a link to them on Canvas. Where did I put it? I think it's under homework. There's a link to sample problems. And you're welcome to look at those, and you're welcome to try the unsolved ones and consult the solved ones and so on. But that's not the homework I'm going to count for this course. Okay? So I'm going to give you homework, and I'm generally going to give it during lecture. And it's going to be based on where we are in the course, what we're lecturing on, what people's understanding seems to be, and so on. And I'll write some problems on the projector, and you'll have to write these down, and those will be the homework questions. Okay? They're probably not going to be posted in Canvas, especially as we move through the course, because these things are going to have circuit diagrams and so on and so forth. So you're going to have to be here in class or have a really good friend who you trust who's in class to tell you what the homework was. Okay? Your best option, come to every class, and when I say here's a homework question, have some way to write that down. You can also go back and watch the video, but that's an hour and 50 minutes of video, right? All right, so you'll have homework questions assigned at least once a week, possibly twice. We'll see how it goes. And in general, I'll collect the homework the next class period, and I'll grade one problem. Okay, and I won't tell you ahead of time which problem, obviously, so you want to do them all pretty seriously. All right, quizzes. I may or may not do in-class quizzes. I haven't decided yet. If I decide to do in-class quizzes, I'll warn you ahead of time before the first one. Okay, but once we've had that first quiz, then all bets are off, and I might do unannounced quizzes. So again, best option, make sure you're coming to class. Which brings us to attendance. I'm not going to record attendance. I'm not going to dock your grade if you don't show up. But because of these things, your grade will probably go down the less you come to class. The most important part of attendance, of course, is that this is where you're going to learn the material. Right? You're going to hopefully think about what we're discussing, ask questions, think about it some more, and then go home and do problems, and that'll cement your understanding. And then the next class, ask about the things you couldn't figure out and so on. That's how you're going to learn the stuff. Okay, so attendance is really critical. Lab assignments, so there's 8 labs. Everybody here had 120 at some point? Okay. So collaboratorium is where you can do your labs. There's 8 labs. You'll be working in groups of 2 to 3 people per group. Okay, we have a total of 8 groups for this section, and probably under 24 people, at least so far. So 2 to 3 per group will work. Lab reports need to be written individually. You're working on the lab with other people in your group. So you're doing the experiments together, you're building the circuits together and so on, but the report that you turn in on Canvas has to be your own writing. Okay? The only thing that you can share from one report to another are things like circuit diagrams. Okay? Drawings that you've worked on as a group. You can take one of those and copy it, or the signature where you get an instructor to sign off saying your lab work, you can copy that. Everything else you should do your own words, your own report. So late labs, 20 points per day. So don't turn them in late. If you turn it in 5 days late, it's going to be a 0, but you got to do every lab to pass the course. Okay, so even if you're a week late and you're not getting any points for it, you still got to turn it in. Exams and quizzes, if we have them, will be closed book. I'll let you have note pages. For exams, midterm and final, you can do 2 pages double-sided. For quizzes, 1 page double-sided, or you can have single-sided, twice as many. You can write them by hand, you can computer generate them, you can Xerox them, you can use mimeograph and make it really small. It's up to you, okay? But closed book. And last detail here, keep an eye on your grades in Canvas, okay? Once I grade things, I'll put the grades into Canvas and then hand back the work to you. Get in the habit of checking Canvas, make sure that you got a grade and it's the grade that you actually saw written. As opposed to, after the final exam, coming to my office and saying, you know, that second homework I did, I think I got an 80 and you only gave me a 70. And if you give me those 10 extra points, I'll go to a B instead of a C, right? And so it's a lot easier to do it while it's fresh and you still have the original and so on. All right. One more administrative thing. 8 things to know about this course. So this is just based on the times I've taught this in the past. I don't know how many times I've taught this course. It's been several. And these are some ideas to keep in mind that I think will help people be more successful in here. So first thing to know about Engineering 250, it's a hard course. Okay? The material is difficult. There's 8 labs. There's 10 chapters in the book. We do at least 8 of those chapters. Okay, and it's a 10-week course. That's pretty fast-paced. And each week we've got 2 meetings, right? So this meeting and Thursday's meeting, we're going to cover a whole chapter, possibly a chapter and a half of the book. And as we move on towards the later part of the course, the material itself gets more complex. We're going to start off with some review of stuff you did in 120 from chapter 5. But it's going to get more complex and it's going to grow quickly. Not an unreasonable expectation in terms of the ideal would be 10 to 15 hours per week outside of class spent on this course. Now, life happens, right? We have more in our lives than just Engineering 250. So this is not always practical, okay? But this would be kind of an ideal. The rule of thumb is anywhere from 3 to 5 hours outside of class for every hour you spend inside. Not always doable, but just to kind of give you an idea, if you're spending 20 minutes a week outside of class on this, it's probably not enough effort, okay? And it will probably make it harder to really learn the material. So the course is hard. Most of the material will probably be new to you, but we're going to start off with a review of some stuff from 120. So don't do what used to happen to me in school. I'd get to a course, I'd listen for the first few minutes, I'd decide I knew everything that was going on in the course, and I'd zone out. And I'd tune back in about an hour later, and I'd have no idea what was going on. And then, of course, I didn't want to ask questions because I was lost, and I figured everybody else knew what was going on. So I'd just sit there and I'd zone out again, and I'd go home and I'd try to learn it on my own, and that wouldn't work. And I'd come back the next class and I'd still be lost, and it would just go downhill from there, right? Don't let that happen to you, okay? So how do you avoid that? Try to stay present, okay? Try to be tuned into what's going on in class. If you find that your mind has drifted, if you find that you've gone somewhere else, just bring yourself back gently to where we are right now. Okay, don't beat yourself up. I'm a terrible student. Why do I do that, right? Just come back and tune back in again. And if you feel like you're lost, even if it's because you zoned out or you were thinking about something else, ask questions, okay? I really, really, really like when students ask questions, because I can sit up here and I can talk for hours, and it's a one-way process. I have no idea if I'm being effective or not, right? Now, if someone raises their hand and says, I don't understand what you did in this step, now I can say something meaningful, right? At least for that person. And if you're confused by something, chances are there's other people in here who are confused also. So you really want to try to get comfortable with asking questions, okay? Okay, you'll learn mostly from the homeworks and the labs. Again, learning by doing. Come to every class on time, stay the entire class, we talked about. Everything we do will build on what we've already done, okay? And this goes along with trying not to fall behind. By the time we get to week 7 or 8, we're using all the stuff that we've learned so far, and we're using it as if we know what we're doing. So if we're confused about what a truth table is or what an AND gate is, we're going to be really suffering in weeks 5 and 6 when we're doing state machines and we're just throwing around truth tables and AND gates as if we've always known what they mean. Ask questions during class, I already said that. Generally won't be extra credit opportunities in this course. There will be one extra credit opportunity at the end if you want to go visit presentations from students at the last Tuesday of the quarter. There'll be a bit of extra credit opportunity for homework. But in general, there's not a whole lot of extra credit. So, so again, don't plan on coming to me the week of the final and saying, hey, is there anything I can do to get some extra points, right? Take that time and try to spend it towards that, 10 to 15 hours maybe for this. This is probably the most important point here. I'm really here to help you succeed. It sounds like a catchphrase, okay, or a marketing line, but it's really true. It's the only reason I get up and I come in here is to try to help you be successful. Okay, that's my goal, that's my job, that's why I get paid, that's why I do this instead of something else. I can't do that by standing up here and lecturing. I can give you information, okay? You can get information from YouTube, you can get information from the textbook. There's lots of ways that you can get information. Standing up here lecturing is one way to do that. It's not magic. I don't have the magic words that impart understanding, okay? What I can do is I can answer questions. Or you can ask me a question and I can hit you with another question in response and ask you to think about things in a different way. Okay, that's how I can help you learn. But it takes both sides. Okay, you've got to put in the effort and you've got to do your side of it and be willing to say, hey, can you explain this differently? Or can you go over that again? Or here's my homework, but it doesn't feel like I did this right. Can you help me with it? Okay, I'm very reachable. I'm in my office most of the day, most days of the week. I'm pretty accessible through email, and I want to help you however I can. So keep that in mind, and if you feel like you're lost or something, don't feel like, I failed, I'll just hide in the back corner and stay quiet, right? Shoot me a note, come see me in the office, something. Okay, and we'll get you back on track. All right, so any questions on any of that? That's the end of my administrative details. All right. I have one more detail though. So this is about note-taking services. So I've been asked to read the following to you. And this is related to DSS, which we talked about earlier. So a student in this class has a documented disability that impacts his or her ability to take comprehensive lecture notes. The DSS office is requesting that someone, preferably 2 of you, volunteer to share your notes. You do not have to do anything different than you would do for yourself unless you choose to. The DSS office will provide you with NCR paper. This is a carbonless paper, 2-part, 3-hole punched lined notebook paper, and you take your notes on that paper basically. After you've completed the class for a day, you keep a copy and you give the student with a disability the other copy. So you don't have to run to a Xerox machine or anything like that. You basically take your notes, but when you're done, you've got 2 copies of them, and you share one copy with the other student. This way you do not have to go in search of a copy machine. If you would rather not use this free paper and want to use a copy machine, DSS will make copies for you. So that's the other option, is you can take your notes to the office and they'll copy them for you. So with that in mind, is there anyone who would be willing to volunteer his or her notes? And then if no, say, if you are interested but not sure of the process or requirements or have questions, please contact the DSS office in Penguin Building 13 for further information, or you can talk to me during the break or after class if you want more details. It's a pretty painless process, and the carbon paper is really cool to work on, and it helps people out. So keep that in mind. Come and talk to me. Yeah?
Also, another easy way to do it is just take a picture of the notes on whatever you do, and then you can just shoot a text or an email to the person.
So you can camera phone it. And also, I am recording video of everything in class, so it will be available, but inside a hour and 15-minute package. All right, so come and talk to me later if you want more information about that. All right, so let's talk about digital logic. So digital logic, as opposed to, is there some other kind of logic? Why do we say digital? Are there things that aren't digital? Analog, yeah. So it used to be everything was analog. Digital was kind of the new thing. So we didn't talk about digital watches or analog watches. We just talked about watches. And a watch was something you wore on your wrist, and it had hands, and the hands would move very slowly, and they point to the hours and minutes, right? And then we started seeing digital watches that had little circuits inside that would cause it to display numbers. So if it was 1 o'clock, you'd see a 1:00, and those were called digital watches. And now those are usually just called watches, and most of them are digital. So there's a combination, digital and analog, because it's got hands, but it's got numbers too. So in 120, we build circuits, and we have resistors, and we have power supplies, and we do these horrible things called KCL and KVL. And we analyze the circuits, and we say, okay, this is 2.34 volts and 0.157 amps, and things like that. That's analog, okay? Analog in some ways goes along with the idea of continuous. The voltage in a circuit could be anything. It could be 0, could be 2.716 volts, it could be 13.4 volts, it could be negative 5.3 volts. In the digital realm, we start to think more of something binary. And so this is the change from chapter 4 to chapter 5 in 120. All of a sudden in chapter 5 we were talking about ones and zeros, right? Lots of ones and zeros, the so-called binary digits. Or bits. It's the same stuff. There's still wires, and there's voltage, and there's current, and there's resistors, and things like that inside a computer circuit. It's the same stuff, but we're interpreting what's going on in the circuit differently. So think about some sort of voltage. And let's say this is 0 volts, and let's say this is 5 volts. And maybe this is time. And we've got some point in the circuit, and the voltage is changing over time. Well, here's what we do in 250. We sort of draw a magic line. Let's just say it's in the middle at 2.5 volts. And we don't worry about, is this 1 volt or 1.2 volts or 1.211 volts. We just worry, is it above or below this green line? And if it's above, we're going to call that one thing. And if it's below, we're going to call it something else. So we're simplifying our view of the world. Our voltages are either high or low. And we usually make things a little more interesting. We might actually have 2 of these cutoff voltages, maybe 4 volts on top and 1.5 volts on the bottom. And we're not going to worry about anything with a voltage in between these. But we're going to say very clearly, anything that's 4 volts or bigger, that's high. And anything below 1.5 volts, that's low. And if we see the whole world as everything is either high or low, it's very easy to represent that. We can represent that with a single piece of information, something we call a bit. So we could use the value 1 to represent high and the value 0 to represent low. And inside our circuits, the AND gates that we use to make an airplane landing controller, for example, there were still voltages moving up and down between 0 and 5 volts. But we ignored all of that and we basically said, is it close to 5 or is it close to 0 volts? And if it's close to 5, we treat that as having a value of 1. And if it's close to 0, we treat that as having a value of 0. And so part of what we're doing here is digitizing. And digitizing is basically converting from analog to digital.
So am I correct in assuming that the application for this is taking the air traffic controller, for example, and you want to plug it into a computer or device some way, and wants to register a 1 or a 0, instead of it knowing, okay, this many volts is a 1, it's, okay, just have something bigger or something lower. It's easier for me to understand the specific number.
Yep.
Okay.
And it takes less to sort of process this, right? If I say, how many volts do you have now and how many volts do you have over there? Well, I got 4.2 volts here and I got 4.6 volts there. How can I do something to say, are both of those voltages high, right? Well, if I say this is high and this is high, it's really easy to say, are they both high, right? They're both high, right? But if this is 4.2 and that's 4.7 and this is 1.1, right, you've got to do more work. So in some sense, it's simpler to do processing with just these simplified 1s and 0s, or these highs and lows. And that's part of why digital logic is in some ways easier to work with.
Yeah, I was wondering, you said it was harder, but this seems like it's almost easier.
Yeah. Although someone who specializes in analog circuits might feel differently. They might say, oh, analog is so easy, KVL, KCL, that's like a walk in the park. And this 1 and 0 stuff confuses me. So it's partially where you're coming from. But to me, this is simpler. All right. So whole course, we're mostly dealing with just 1s and 0s. Okay, highs and lows, 2 things basically. And we can think of them in different ways. So we typically think about 1 and 0, and we sometimes call this high and low. Or we can think of this as on and off, or yes and no, or true and false. And there's other ways that we could do this. We could call this paper and plastic. They're just labels, right? The essential truth, though, is that there's 2 bins here. And in some cases, we might actually, in this bin, say that this is false, and the 0 bin is true. It's something called negative logic, and it's pretty common. And it trips people up because we get so ingrained with the idea that 1 is high, is on, is yes, is true, right? But it's pretty arbitrary.
Sorry, but why would you ever reverse true and false if you just instead reverse 0 and 1? Isn't that a lot easier?
You could think of it as reversing 0 and 1.
Okay.
It's kind of the same thing. And we'll talk about duals later, and we'll see that like all this stuff is artificial at some level.
Is there different ways of referring to it just depending on the situation or something, or depending on the system?
Yeah, but it's a little subtle. It's really that everything that we say about 1s and 0s, we can make a similar statement about 0s and 1s. When we start talking, well, you've done AND gates, right? So we talk about ANDs as something which is true if all of the inputs are true. Well, we could define an AND gate as something that's false if all of the inputs are false. And it's really no different from an AND gate. If we completely switch our mindset, where we swap false and true, it turns out it's exactly the same logical function. But sometimes, for reasons of how these devices are actually implemented, you may prefer to have lots of 0s versus lots of 1s. And so it may be advantageous to go to negative logic. If you want fun, go online and go into Google and type something like, why is negative logic stupid? And make some popcorn and then just like read all the people ranting about why it's horrible or why it's like brilliant. And people get really kind of philosophical about it.
In the long run, is it to save energy?
That could be a factor, or it could be speed, or it could be convenience, or it could be engineering convention. Because certain types of systems tend to use negative logic, and devices that you can get are described in terms of negative logic. And so if you design your circuit using that same mindset, then you don't have to do this conversion.
This might be a dumb question, but so if we are doing binary logic as in it's above or below a certain number of volts, could you have, for example, 0 being no volts and then 1 be any volts?
You could, but here's the thing. So here we've got this, what's called this forbidden zone, right? This band in between. If we don't have that, if we have something like this, and let's say that our dividing line is right here. So this is a 1 and these are all 0s and this is a 1. These circuits, since they're actually analog circuits inside, they're imperfect. We can talk about them theoretically, but in practice they're imperfect. So here's what your circuit is outputting, but all of a sudden somebody turns on a hairdryer in the next room and the motors generate electromagnetic radiation, and the circuitry that's generating this picks that up and changes it into voltages, and now your waveform does this. Gets just a little more voltage in this one spot, and suddenly we think we've got another 1 here. And that can make a huge difference, right? Getting 3 1s might mean something that we didn't intend to mean. So by having this forbidden band, if this goes down a little bit, or this goes up a little bit, right? It doesn't change the logic value. So along those lines, if we said 0 or not 0, we'd have sort of the same problem. Because this thing that's supposed to be a 0 might bump up a little bit.
So reasonably you could, just logically you can't, because there's always going to be some factor that you can't control.
Yeah. So you want, so it's basically a noise tolerance.
Yeah.
Because these circuits are noisy internally. They're imprecise. And it's not always 0 to 5 volts, although in this course it is. Well, most of the time in this course it is. But more and more, this upper voltage level has dropped. So inside a modern computer, your high voltage might be 1 volt. It might be 0.8 volts. And that's a power saving thing, right? Trying to drive an output from 0 volts to 5 volts takes more power than driving it from 0 to 0.8 volts, right? Power voltage times current. So the voltages have shrunk. But as the voltages shrink, the width of this forbidden band also shrinks. So with this, if our voltage changes by half a volt, we're probably okay.
So why not just decrease the maximum voltage to something really low, like 0.5 or something, to save a ton of power? It's just that's not possible.
That's what they do, but if you make it too small, then you are subject to noise issues. So it's a balancing act. You want a low voltage so you get lots of fast switching without too much power, but you still need a good band of protection so that if something spikes your power supply, it doesn't change your zeros and ones. And we'll see this in one of the labs. We'll do one lab where we're actually working with analog circuits. We'll be working with motors. And if we don't take careful steps, the motor, when it's running too fast, will actually interfere with what's going on. That'll happen in 270, not this course, but we'll see that. All right, so what do we do with all these ones and zeros? We can represent ones and zeros with voltage levels. Mostly, we want to process information in some way. We want information about which airplanes are where, and we want to generate information about which one should be allowed to land. Okay, or we have cars on a roadway, and we want to know which cars are present and decide which one should get a green light, which one should be red. Okay, that'll be where a lot of your early labs are spent, is a traffic light controller. So we're processing information. And this brings up the question of representation of whatever. We'll just say information. But we work a lot with numbers, because this is kind of computer stuff, right? Computers and math seem to go together. But we can represent pretty much anything we want using ones and zeros. But we've got to work at it a little. How do we represent a 2-hour movie using ones and zeros?
Lots of ones and zeros.
Lots of ones and zeros. But it's no different from what we do. We can represent emotions and dreams and acts of war and all of this stuff with a handful of characters. It's called the alphabet, right? And by putting these characters together in certain orders, and by having a common shared understanding of what these things mean, we can represent all kinds of things, ideas and thoughts and recordings of events and so on and so forth. And we can represent pictures with ones and zeros. Every time you take a picture with your phone, this is what's happening, right? It looks like a picture, but it's really a bunch of individual pixels. And if it was purely grayscale, if it was purely black and white actually, each pixel would be either lit or not lit. And if your pixels are small enough and you have enough of them, you can make a black and white picture. Well, you throw in a few more bits to represent colors and you can get a full color picture. And when you paint with oil paints, is that digital? Not really, but in some way it is, because these paints eventually come down to molecules or maybe atoms. There's no oil color atom, but it comes down to at least molecules, these individual pieces of matter that have color and are being placed on a canvas, right? And it's really not continuous. It's really just very, very, very finely digitized. So we do this all the time, right? So let's talk about numbers. Let's talk in particular about integers. So whole numbers. Well, if all we have in our world is a 0 and a 1, we can only represent two things. Maybe the numbers 0 and 1, maybe the numbers 5 and 7. Okay? But by taking combinations of zeros and ones, we can represent more things. So here's one example. If I have 3 ones and zeros, there's 8 combinations of them, assuming the order is important, which it is. And I could decide, okay, this is going to be the number 5, the number 2, 3, 1, 14, negative 66, 42, and 1,000. Is that a valid way to represent 8 numbers using 3 bits? Absolutely. Is it particularly useful? Probably not. But it's a representation of 8 pieces of information using combinations of 3 ones and zeros. It's perfectly valid, but it's not what we typically do. A more typical example would be this. And you probably recognize this from 120, right? And this is actually a very natural way to represent numbers from 0 through 7 using 3 bits. And if you talk to anybody who knows digital logic and you ask them what the number 5 is in binary, they'll probably say 101. But why do we use these particular patterns to represent these numbers? Do you remember?
Because 2 is being squared.
Okay, expand on that.
The first number starting from the right has an exponent of 0, and then it goes to 2 to the 1, and then 2 to the 3.
There you go. So each column represents a power of 2. This is 2 to the 0. This is the 1's column. 2 to the 1 is the 2's column. 2 to the 2 is the 4's column. And we use this handy scheme. If we have a 1 in a column, we add whatever that power of 2 is. So 101 means we want a 4 plus a 1. That gives us 5. Okay, so the technical term for this is weighted positional notation. And it's still just a representation. It's a mapping from 1s and 0s to integers, but it's a really useful one. Because it turns out if we use weighted positional notation to write integers, we can do arithmetic on integers. And we can do arithmetic the same way we do arithmetic on decimal numbers, we can do it on binary numbers. And we can compare decimal numbers the same way we compare binary numbers. We can look at 2 binary numbers and tell which one is bigger in the same way that we do this with decimal. We find the first digit that's different, and whichever one has the bigger digit, that's a larger number. So mostly we'll deal with weighted positional notation, but not always. And keep in mind there's nothing inherent about this that makes it better or worse than this, except that it's a whole lot more useful. So mostly review so far? Okay, good. Well, we're going to be dealing with things like computers in here. Not full-blown computers, but circuits that would be used as part of a computer, for example. Or maybe not, right? Maybe just circuits that work in place of computers to do control of systems and such. But we're working with systems that are not smart, okay? You and I, we're pretty smart. I can write down this number, and we all know this is 1,473. And I can write down this number, and we all know that's 25. And I can write down this number, and we know that's 101. Computers cannot do that. There's a few problems with what I just wrote. For one, this thing I used 4 symbols, this thing I used 3, this thing I used 2. Did that trip anybody up? Did that disturb anybody? Probably not. I also happened to put this over here and this one on the right and this one on the left, and I put them at different heights, and this one's angled slightly. And none of that bothers us, right? That's because we got this like awesome processing thing in our head. Computers will have a horrible time with this. So when we deal with binary numbers, one of the things we have to kind of standardize is how many bits are we talking about. And in this case here, I was using 3 bits to represent integers. If I wanted to feed a circuit the number 1, I can't just feed it a 1. I've got to feed it a 0, 0, 1. Okay, so we're going to need to keep that in mind with what we're doing after the break. We're always going to have to stick to a fixed number of bits to keep things reasonable.
That's like 64-bit computer or something. Does that mean it has a line of 64?
Exactly. So when you have a 64-bit machine, it means that all your numbers are the same length, typically 64 bits. Even if you're just storing the number 5, it's not going to be 101. It's going to be 101 with 61 zeros hanging off that left digit. And it's kind of a waste, but there's really no easy way around that because computers aren't that smart. They can't look at this and say, oh, there's extra zeros in the front.
What's the advantage of having a 64-bit system instead of a 32-bit system that just so they can handle larger numbers? Is that it?
For a while, it was about the number of bits in your integers or your numbers. But at 64, that's not really the big issue. It has a lot more to do with memory. If you have a 16-bit computer, you can use 2 to the 16th different memory locations. So 65,000 memory locations, 64K. That was the old benchmark for early mini computers, microcomputers. 32-bit computer, you can access 2 to the 32nd location. So how big is 2 to the 32nd? Anyone know? It's a big number. You got a calculator.
Okay.
Yeah. So it's about 4 billion, right? And it used to be that was plenty big, right? You'd never have a hard drive that could hold 4 billion bits of information, right? Yeah. Now you have a flash drive that, you know, blows that away. So 64 bits gives you more addressing. But there's other reasons having to do with computer architecture and how you set up pipelines and how many things you have to pull from memory at a time and so on. But for smaller numbers, it's largely about, you know, having a single 32-bit thing that can hold 4 billion different integers. And same with floating point. We'll talk about floating point in a few weeks. But it's another representation of things with strings of bits. All right, so let's do a 5-minute break. Let's come back about 1 o'clock, and we'll look at different ways to represent integers. We'll start talking about negative numbers, and we'll talk about non-integer numbers.
Just want to let you know, my class right before this ends at 11:50.
Okay.
And it's in Bower Hall.
Oh, fun, yeah.
So I'm going to be a couple minutes
fine.
later.
Yeah, don't worry about
I'm
that.
going to get some exercise.
Okay, yeah, thanks for letting me know.
Yeah.
Yeah. Well, that's the thing is, man, I haven't really, I started reading chapters No, yeah, because I started until like 9 o'clock and then about like 10:30 to like 20.
All right, so let's talk more about representing integers. So we've got weighted positional notation, and I'm going to stick with 4 bits for this part of the class. So we're always going to deal with 4-bit numbers. And there's a way to write down all the combinations of zeros and ones. So how many combinations of zeros and ones are there if we've got 4 bits to deal with? 16. How do you know that? Right, so it's 2 to the 4th. So if you have 8 bits, you've got 2 to the 8th possibilities, 256. So it's always 2 to the n, different ways that you can arrange n zeros and ones. And if you want to make a table of how your 0 and 1s map to different integers, there's a particular order you write your zeros and ones in. And sometimes you memorize this in 120, sometimes you figure out a system for doing it. Let me show you a system that I use for doing this. So if I only have a single bit, it's really easy to write down all the possibilities. It's just a 0 or a 1. Agreed? Okay, if I'm going to have 2 bits, here's what I'm going to do. I'm going to repeat this pattern. And on the first half of these, I'm going to put a 0 next to it. And on the second half, I'm going to put a 1 next to it. And there I've got my 4 combinations of zeros and ones for 2 bits. Now if I want to go to 3 bits, I'm just going to take this set of 4 possibilities and repeat it. And on the top half I'll put a 0 on the left, and on the bottom half I'll put a 1 on the left. There's all my combinations for 3 bits. And if I want 4-bit numbers, I'll just copy that down. And I'm just putting these lines to keep things lined up. And on the top half I'll put zeros. Bottom half I'll put ones. And there's your 16 combinations. Now an advantage of doing it this way is if I try to write down what integer these correspond to, they're in the right order. And eventually you memorize these things, and 1010 just means 10 to you. But until then, right, you can make tables like this. And if I wanted a 5th bit, same thing, just copy this down. Top half gets a 0 on the left, bottom half gets a 1. There's your 5-bit numbers. So we can switch between bits and integers pretty painlessly. So this is decimal. So did you talk about octal numbers in 120? Raise your hand if you talk about octals. So what's the idea of an octal number? The idea is that if I say, okay, I want to tell you what my credit card number is, are you ready? And you say, yeah. And I say, my credit card number is this, and I'm reading this to you on the phone over a cell signal that's kind of spotty, you're probably not going to get the right number, right? We don't do well as humans dealing with 1110101110. Computers, they love this, right? That's what computers are built to do, is process ones and zeros. People, we don't do well with that. So we could instead rephrase this by breaking this up into groups of 3 and using a more interesting sounding symbol for each of these groups. And so we can talk about octal notation. In octal notation, we're basically taking a big string of 1s and 0s, we're breaking it into groups of 3, and we just write down the decimal digit for each group of 3. So 011, that's the number 3. 101, that's our 5. 010, that's a 2, that's a 6, and so on.
So this is different from hexadecimal?
This is different from hexadecimal, but it's the same idea. We're doing hex right after this.
Okay.
So we could take this big long number and we could say that this is equal to 6253 octal, right, plus some other digits that I didn't list. And sometimes instead of writing the word octal, we put a little subscript 8. That means base 8. And it's 8 because the numbers that we can write here are everything from 0 through 7. And sometimes for decimal, we just put a period at the end to say this is a decimal number. Or we could write a subscript 10 to say it's base 10. So what would this number 1000 be in octal?
0.
So these 3 bits would be a 0. And then what do we do with this 1 sitting right here?
1.
That's going to be a 1. And we can sort of imagine that there's 2 extra zeros, because if we stick more zeros on the left of a number, it doesn't change the value, right? Just like the number 23 is the same as 00023, it's still 23. So if we wanted to write these numbers in octal, right, this number would be a 1 followed by a 7. And octal was popular for a while in the earlier days of computers. But as we moved to wider words and we deal with 32 or 64-bit quantities, there's a problem with octal. Octal breaks things into groups of 3. 32, 64, 16, those are not multiples of 3. So you always got this extra bit hanging off somewhere.
Sorry, I'm just copying this minute. I missed why this happened. But why is there no 8 or 9 in octal?
Because we're breaking this number into groups of 3, and the largest number you can get with 3 bits is just a 7.
Okay.
Right? If there's a 4th bit here, that's going to be the next octal digit.
Gotcha. All right.
Well, we can go in the other direction, and we can talk about something called hexadecimal, which is base 16. And in hexadecimal, we break our number into groups of 4 bits. And it turns out it works better to break things into 4s rather than 3s. Because 16, 32, 64, these are multiples of 4, and 4 itself is a power of 2. So in hexadecimal, we write down the digit corresponding to each bit of 4, each set of 4 bits. So 1001 is a 9, 010 is a 6, but 1110, that's the decimal number 14. And we don't want to write a 14 here because we don't know if that's 14 or if it's a 1 and a 4. So here's how we code hexadecimal. If the 4 bits are anything from 0 through 9, we just write a 0 through 9. But if the 4 bits are 1010, which is a 10, we write the letter A. And if it's a 1011, 11, we write a B. And similarly, C, D, E, and F. So if we wanted to take this number and represent it in hexadecimal, we break it into groups of 4 bits. And we write the hex digit corresponding to each of these 4-bit patterns. So 1111, that's an F. 1010, that's an A. 0111, that's a 7. And 1001, that's a 9. So this whole set of 16 bits could be written as 97AF, and we can write it base 16, or we can write 97AF, and sometimes we just put an X as a subscript, and that means hexadecimal. Or in a programming language, we can say 0x97AF. And the book does something with an H. I think it's maybe they do that. I don't know. But if you see a number with an H in the beginning or the end, it's probably hexadecimal. Check the book and see what it's doing. But this is the most common one in digital logic, and this is the most common one in programming.
Okay, so X could also just represent 16. X doesn't matter.
Yeah, X basically means that the number here is hexadecimal. So each of these represents 4 bits.
Push back on the octal. Is it? That's basically the same thing you did, but with 3.
Exactly.
digits
It's exactly the
replaced.
same idea.
Okay.
So octal, you break it into groups of 3, and we just write the digits 0 through 7,
Okay. Yeah.
right? Hex, we break it into groups of 4, and we write the digits 0 through F. Binary, we break it into groups of 1, and we write the digits 0 or 1. That's what a binary number is. So those are different ways to represent binary, and it's useful to be fluent in them. As you move on towards 270 microprocessors. How many people here are taking 270 in the summer, by the way? I think they are. Okay. Yeah, registration comes fast. It's shocking. As we move towards doing more and more with this, and eventually moving into microcomputers and 270, we work more and more in hex. Oh, these? So we just say 0x to say that the stuff that comes after represents a hexadecimal number. So in a programming language, when we want to say this variable is equal to some number in hex, we can't put a subscript of x or a subscript of 16. It's just not part of the character set. So the convention is if you have a 0 followed by an x, that says this is a hexadecimal representation. And most modern languages use that convention.
I could be wrong. If I remember correctly, is it one of the most common places you see hexadecimal outside programming, like Photoshop, for example, represents colors? Hexadecimal.
Yeah. And it doesn't have to, right? You can use 0 through 255 for each color, but ultimately it turns into hex or it turns into binary. So it's represented in hex usually. And if you do things on your computer, if you set up a wireless connection or you install a piece of hardware and you start looking at drivers and addresses, you always see things with lots of Fs, right? Fs are bunches of ones strung together. And yeah, which is black for, well,
Or is it white?
it would be
I was
white.
getting mixed,
Yeah.
white.
Unless it's negative. But we'll see now why there's so many ones that pop up in these things. So okay on representations? All right, cool. So let's talk about negatives. So everything we've done with weighted positional notation is great if we want to represent positive numbers or 0. But we got to have negative numbers also, right? That's one of the breakthroughs of civilization, was being comfortable with negative numbers, which logically makes no sense, right? Talking about a negative cow added to a positive cow gives you nothing, makes no sense, right? It doesn't correspond to anything in our experience, but conceptually it's a really powerful idea to be able to have a negative and understand that 5 apples plus negative 2 apples gives you 3 apples, right? So that conceptualization was huge in our development, and we want negative numbers in digital logic also. So we're sticking with a fixed number of bits, let's say 4 bits. So I said we can do arithmetic with strings of bits, just like we do with decimals. So for example, suppose I want to do 5 plus 7. Well, here's the number 5, here's the number 7. Let's add them the way we would in grade school. 1 plus 1 is 2, but 2 is not a number, right? 1 0 is 2. It's actually 0 with a carry of 1. Right, just like 7 plus 3, we write down a 0 with a carry of 1. So 1 plus 1 is 0 with a carry of 1. 1 plus 0 plus 1 again is a 0 with a carry of 1. 1 plus 1 plus 1, well that's 3, which is 1, 1. So this is a 1 with a carry of 1. 1 plus 0 is 1. And guess what? This is equal to 12. So addition works the way we normally would. If you want a less convoluted example, here's 2 plus 5. And it gives us 7. And we can do subtraction the same way. We can subtract and we can borrow, but subtraction is always harder than addition for some reason, right? Like division is harder than multiplication. We can multiply these two, by the way. We can do pencil and paper multiplication, and it works great. But subtraction, instead of doing, subtract 1 from 1, subtract 1 from 0, and borrow 1 and all that, subtraction is really the same as adding a negative. If we wanted to compute 7 minus 5, that's actually 7 plus negative 5. And if we had a way to represent negative 5, we could use our same knowledge of addition and just add 7 and negative 5, and that would give us what 7 minus 5 is. So we want a way to represent negative numbers And again, there's lots of ways we can do this, but there's one particular way which is very useful, and this is called 2's complement. So let me give you a procedure for finding the 2's complement of a number, and we can talk more later about why this works. So here's an example. Find -7. So first thing you do is you write down +7. And it's important here, if we're working with 4-bit numbers, that I include that leading 0. Okay, the most common place where people go wrong with 2's complement is they forget to put in those extra zeros to make everything the same number of bits. So I want the number +7 is 0, 1, 1, 1. Okay, so that's step 1, just write down +7. Step 2, complement everything. Change your zeros to ones, change your ones to zeros. So that gives me 1, 0, 0, 0. And then step 3, add 1. That's my 2's complement notation for -7. And for starters, we can just take this as this is what we do without really knowing why this makes sense. Well, we can talk later about why it makes sense. But as a procedure, if we know how to write a positive number in binary, if we complement all the bits and then add 1, that gives us the binary representation of the negative version of that number.
How does the computer recognize -7 versus 9?
It turns out that anytime we have a negative number, this first bit's going to be a 1.
Why couldn't that also just be 9?
Because when we allow negative numbers, 9's not something we can represent with 4 bits. With 4 bits, we can represent -8, -7, -6. All the way up to +7. But we're basically shifting our range of integers. There's still 16 different integers we can represent, but they start at -8 and they go to +7, instead of starting at 0 and going to 15. Do you have a question?
That was basically my question, but, so you sort of have to know ahead of time whether or not negative numbers are allowed then?
Absolutely.
So
Okay, that was
is that like declaring an integer is assigned or unsigned?
Same thing, yep, that's why we do it. So inside the guts of a computer, it doesn't care, it just sees bits and it's going to run them through an adder. But to us who are interpreting these bits as integers, we need to know, is this the number 9 or is it the number -7? And it's kind of a human construct on top of what the computer cares about. All right, so let's find -2. So what's our first step? Okay, so write 2, +2 in binary, so what's +2? 0, 0, 1, 0, good, and you got the leading zeros. Excellent. Okay, next step, complement. So what's the complement of 0, 0, 1, 0? 1, 1, 0, 1. That's the easier piece. And then step 3, add 1. So that'll be a 0 with a carry of 1. 1, 1, 1, 0. That's -2.
So then to reverse that, you would just remove the 1, or subtract, oh, we can't subtract 1.
Can't subtract 1.
So you reverse it by adding -1.
It turns out it's pretty easy to reverse this if we complement it and add 1.
Oh.
Get back to where we started.
Just do the exact same thing again.
Yeah.
Oh.
So taking the 2's complement of a number gives you the negative version of that number. So if we take the 2's complement of -2, we get the negative version of -2, that's +2.
So with the negatives, they never go above 8, period? Or do we have negative numbers?
With 4 bits, negatives will never get smaller than -8, and positives will never get bigger than 7.
Okay.
But if you have 32 bits, you can go from about -2 billion to +2 billion.
And to clarify, that's only if that computer is able to understand negative.
Mm-hmm.
So if it doesn't, it'll be from 0 to 15. Not 0 to 15, 0 to
4 billion or 15, 15 or whatever, yeah. But again, this is really just how we're interpreting these ones and zeros. The computer really doesn't know what it's doing. It's just taking these things and running them through an adder, right? And we'll build an adder circuit in one of our labs, and we'll be putting in bits. Are they all positive, or are they positive and negative? Not going to make any difference, right? Except how we decide to interpret it. All right, so let's find -0. So what's the number 0 in binary? 4 zeros. Complement it. That's 4 ones. Add a 1. There's a 0 with a carry of 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 1. We have an extra 1 here on the end, but we only have a 4-bit result, so we don't do anything with an extra 1. So this is -0, which gloriously is exactly the same as +0. So that's a good thing. All right, let's do one more. -5. So there's 5. If we complement, we get 1 0 1 0. If we add 1, we get 1 0 1 1. That's -5. Okay, so let's see if this is worth anything. Let's calculate 2 minus 7. Well, the number 2 is 0 0 1 0. That's +2. The number -7 we computed was 1 0 0 1. And if we add these together, we get 1 1 0 1. And 1 1 0 1, that's -5. So we've just calculated in binary 2 minus 7 is equal to -5. So our arithmetic still works. And that's the whole point of doing 2's complement. So that just takes some practice to get used to, but most important thing, make sure you keep the same number of bits. Right? Let me show you what happens if you don't. I'll do this in red because this means don't do this. So this is bad. Right, that's not -7. Okay, so you really need, here's good. You really need 7 equals this. Complement it. Add 1. That's -7. All right, so let me give you some homework questions to practice on, and then we'll talk about lab 1. So let's see. Oh, we didn't talk about converting to binary yet. Yeah.
Are we going to be turning in the homework?
Say again?
Are we going to be turning in the homework?
Yeah, so here's what I want to do. I'm going to give you some questions to work on, and Thursday we'll start off by talking about the homework. and we'll see how far you got, and the ones that people are having trouble on, we can work through in class, and you can work on them. We'll spend about 20 or 30 minutes in class working on homework, and then you can turn in what you've done, right, including what you did in class. But we haven't talked about converting to binary, so let's convert to decimal. So for question 1, convert these to unsigned decimal. Forget about 2's complement. Okay, just convert them to a positive number that they correspond to. For part 2, convert those to signed decimal. Those are all 8 bits. And for part 3, write each of those 3 numbers in hexadecimal and also in octal. Does that make sense? Do a snapshot of that just because. All right, so work on those and we can talk about them on Thursday. Let's talk about the first lab. So your labs are posted on Canvas. And if you've seen the old syllabus for this course, don't use the old syllabus, okay? Because the old syllabus pointed to different labs, pointed to different homeworks, and so on and so forth. So I've got a link here to Lab 1, but it's basically this. All right, so first thing, as I said, we have 8 groups for this course. There's a cabinet in the collaboratorium that says Engineering 250, 270, I think they're grouped together. And I'll put this sign-up sheet on the door of the cabinet. What you want to do is talk amongst yourselves, find people you want to work with, and put yourself into groups of 2 or 3 people. And then go to the sign-up sheet on the cabinet door and put your names there. I'll ask you to print your full names, please, so that I can read it and record who's working with who. And then that'll be the number of the parts box that you use, same as you did in 120. And it should have stuff in there that you need for the labs. So let me talk about Lab 1. Lab 1 is a bit of a refresher on some stuff from 120 and also a bit of an introduction to some 250 specific stuff. So experiment 1, you want to basically familiarize yourself with the equipment in the collaboratorium that you'll be using. 4 main pieces of equipment: power supply, which you're used to, right? That's the thing that generates voltage. multimeter, which you also use in 120 for measuring voltage, current, resistance, and we'll mostly use it for measuring voltage in this course. Something called a function generator, and that may be a new piece of equipment to you. That's a system that is used to generate signals that change over time. And we'll use it mostly to generate signals that go high and low, typically 5 volts and 0 volts. So we can generate a stream of logic ones and zeros. And you can control how long it stays high, how long it stays low, so the frequency that it generates and so on. And this fourth piece of equipment, the oscilloscope, this one we don't do a whole lot with, but it's probably the most valuable piece of equipment in the room. It can be used to look at a signal that's changing in time. Now if you have a circuit and it's putting out 5 volts, you can take a multimeter, measure your circuit and see a 5, and you know, okay, that's high. But if your system is generating an output that's changing, it's hard to use a multimeter, especially if it's changing 1,000,000 times a second. Right? You can't catch that from looking at a multimeter or hooking up an LED and seeing if it's on or off. An oscilloscope is a piece of equipment that will show you a picture of your signal versus time. It basically plots it for you. And it's a really cool piece of equipment to get comfortable with. So here's the power supply. You've worked with this before, right? Your goal in experiment 1 is basically you want to identify what the different controls, the different knobs and buttons and displays are on each piece of equipment. You're not trying to recreate the instruction manual for this. You're just trying to sort of learn a little bit about basic operation. So for example, on a voltage supply, there's this thing over here that says volts and amps. Do we know what that does? Maybe we do, maybe we don't, right? It would be useful to find out because it's usually in the volts position, sometimes it's in the amps position. And if you have no idea what this switch does, you might think your circuit is broken. And it's not. This is changing what it's displaying. Is it displaying voltage or current? And sometimes this red light comes on, and sometimes it means there's a problem in our circuit. Sometimes we turn knobs until it goes off. Sometimes we get a different power supply, right? But what does that red light actually mean? So you want to take this experiment in the lab as a chance to sort of drill down into some of these things. Okay, you're going to be using this a lot in 250. You're going to be using it in 270. If you're electrical engineering, you're going to use it in your following 3 courses as well, 204, 252, 253. So it's worth understanding. This is positive, this is negative, this is ground. What do those mean? Right? If you've ever taken a plug from ground and hooked it up to your circuit and had your circuit not work, you know what ground means. It does not mean the same thing as 0 volts. It's what's called a case ground. So for each of these parts in experiment 1, your goal is basically just draw a little sketch of the front of the piece of equipment and play around with it, figure out what the different controls do, and document a few of them. You don't have to document every single aspect, especially with like the oscilloscope, which has tons of knobs and dials in the front. But the basic ideas, okay? So for the multimeter, at least talk about resistance, voltage, current measurements, and range control. So let me show you what some of these things look like. I don't have a multimeter picture, that's okay. So this is the function generator. And there's not a whole lot going on up here. It's all computer controlled. The setup and stuff is done through a series of a few buttons. And it's got menus that it brings up. But basically you can use this to generate an output voltage that waggles up and down. The oscilloscope will actually draw you a picture of what your waveform is. And so in this setup there was a signal being fed in through this cable to the oscilloscope, and it was a sine wave that was being generated, and it shows that. Now there's a button that says auto setup. I think it's over here. If you pop that, it usually does everything for you. But it's useful to sort of know what some of these other things do. So on Canvas, I put a link into some videos that Izad has made. So some useful engineering 250 videos. And you have to do some looking in here because it's not just 250, it's all of his engineering courses. But somewhere in there, there are videos that go through the operation of each of these pieces of equipment. And that's a good starting point. Okay, you can also find documentation for these things online. You can also come and grab me anytime that I'm in the lab or I'm in the office and say, hey, can you show me how to use an oscilloscope? I'll be happy to help you do that. It's almost impossible to hurt the equipment within reason. Okay, the oscilloscope is a bit of an exception because the way that you connect this cable to the oscilloscope, it's a bit of a funny connector. You don't just push it on or pull it off. You push it on and there's a little ring that you turn, and when you turn that, it pulls the connector in tight. And to remove the cable, you have to turn that until the connector pops out a little bit, and then you can remove it. If you wrap the cord around your hand and you yank, that will also remove it, but it won't go back in. Okay, and I've seen this happen 1 or 2 times. So you don't want to use excessive force. Okay. Similarly, you don't want to throw these things against the wall, right? Or stand on them, or obvious things like that. And you probably don't want to connect them to like 120 volts coming out of the wall. Okay. But in general, fiddling with the knobs and the buttons and stuff like that, you can't hurt it. Okay, and a really good way to get familiar with this is to just play with it. Particularly the function generator and oscilloscope, since those are new, you can hook those together. And you can take the output of the function generator and feed it to the input of the oscilloscope and use this to see what the generator is generating. Okay, and that's a good way to spend a bit of time. That's how I spent part of my childhood, actually. Sorry. All right, so that's experiment 1. So you're exploring these and documenting what you've discovered. Experiment 2 is working with the function generator and the oscilloscope. So 2, 3, and 4, you're basically setting the function generator to make a square wave. So high, low, high, low, high, low, equal amounts of time, high and low. And you can control the frequency. So for experiment 2, you want to set the frequency to 1 kilohertz, which basically means that your output's going to look like this. It's going to go between 0 and 5 volts. It says 50% duty cycle. That just means it's on for the same amount of time that it's off. And this is going to be 1 millisecond. So it's going to go up and down 1,000 times a second. So 5 volt peak to peak with a bias of 2.5, that just means this is 5 volts from here to here, and the low part is at 0 volts. The middle part is at 2.5 volts.
So bias is the separating off.
Bias is it's really an offset. Normally we would think of a signal as being symmetric around 0. So we're saying let's just add 2.5 volts and it makes it look like this.
Oh.
But if we were thinking of splitting it in half, yes, that would be the dividing line then. So experiments 2, 3, and 4, you're going to do this for different frequencies. Experiment 2, 1,000 hertz. Experiment 3, 10 hertz, very slow. Okay, it goes high and low every 1/10 of a second. Experiment 4, you want to set the function generator to the highest frequency possible. It'll probably be in the megahertz range, so millions of changes per second. And when you look at the oscilloscope output, you should see something like this, but it's not going to be exact. You're going to notice things. You might notice that it curves down a bit at the end. Let me exaggerate it. It might look like that. Or you might notice that when it comes down, it does what we call ringing. It goes a little negative and it oscillates and then it settles down. And at different frequencies, you'll see different versions of these effects. So this is all about observation, right? This is science. So you want to do these different configurations and see what happens, what the waveform looks like, and you want to document it. So that's experiments 2, 3, and 4. Experiment 5 you did in 120, map protoboard connectivity. So you get a protoboard and you get a multimeter, you put it on ohms, and you figure out which holes are connected to which. And you've done this before, it's the same protoboard. But that refreshes your memory on how the protoboards are set up. All right, experiment 6. This is one of a multi-part experiment on designing a traffic light control system. So let me show you the setup that I want you to stick with. So think of a three-way intersection that looks like this. And this is west, and this is south, and this is east. All right, so it says a three-way intersection needs a traffic control signal. Each direction has only one lane, so it's kind of a dysfunctional road, and it has a single control light, which is either red or green. There's no yellow lights.
Do you really need one lane, or do you need one lane in each direction?
One lane. It's kind of a comic book version of a three-way intersection.
Because then you don't even, there's nowhere to go.
Yeah.
You can only go up to the intersection, you can't go anywhere.
Yeah, you can go down the road. You can go in either direction on the roads, basically.
Oh, so this is
So-
two-way.
So yeah, so you're allowed to go. Yeah, it's not a one-way road. It's
Okay, yeah, I thought you were saying all 3 roads are one way towards the intersection.
No,
So
no.
I was like,
Yeah, that would be really dysfunctional. No, but there's not like a left lane and a right lane, right?
Okay.
So it's just a free for all. So you want to make a system ultimately that's going to control these lights. So you're going to have a green light on each of these, and you're going to have a red light.
this is it.
You'll have a green light, and you'll have a red light. And your goal eventually will be to design a circuit that, based on whether there's a car present on these sensors, so these are car sensors, figures out which of these lights should be green, which ones should be red. And it's kind of like the airplane landing system, but it's on the ground instead. So we're not going to design this circuit for this lab. What you want to do is think about this and come up with an outline for a control system. Okay, so Thursday we're going to talk more about like coming up with circuits and system diagrams and things like that. But you talked about system diagrams in 120, right? It's sort of the 30,000 foot view of a circuit. So it's a box, it's got inputs and it's got outputs. Right, so system diagram. Inputs, which might be your 3 car sensors, and outputs, which might be your 3 green lights and your 3 red lights.
For the labs, are there going to be class time, or are we just going to go?
It's on your own, so it's in the collaboratorium any of the hours that it's open. So you want to develop a system diagram, which means you need to come up with names of variables for these sensors and for these lights. And you want to make a diagram that shows the inputs to your circuit and the outputs of your circuit. And we're going to talk about truth tables on Thursday, but eventually you're going to want to describe truth tables that map these inputs to outputs. Okay, but you can do the rest of the lab before Thursday, and Thursday we'll move into truth tables. So input and output variables, sketch the intersection, and develop a truth table for the control. Okay, and you're supposed to do this using the right-of-way laws for Washington. So what are the right-of-way laws for Washington for a three-way intersection?
First come, first served.
No.
Right first.
One on the right gets priority.
So for a three-way stop sign intersection.
Stop sign would be first come, first serve.
It is, yes, but if there's a light intersection, there isn't right away laws.
In Washington, I think there is.
There isn't.
Well, for this course, there is.
That's my job.
Okay. All right. So in Washington ++, Car on the right gets priority. Okay, so if there's a car here, it gets to go before this one or this one. If there's a car on the south, it gets priority over west. If there's no cars on east or south, then the car on the west gets to go. Okay, so we'll talk about how to develop truth tables for that. I got 2 minutes left. Let me say something about lab reports. And I have some verbiage on Canvas. I do not have verbiage on Canvas. What's the idea of a lab report? You're doing these labs, you're building circuits, you're coming up with diagrams, you're answering questions and so on, okay? The lab report is how you present what you've done to the world. Think of it as a publication, something that you would write and you would publish in a journal, and other people around the world will read and try to reproduce your results. Okay, it's the basic process of science. And when you go through a lab and it says something like, hook the signal generator up to the oscilloscope, set it to 1 kilohertz, and sketch the waveform, if all you have in your lab report is a drawing of a waveform, and you don't mention that you had a function generator set to a square wave of 1 kilohertz connected to an oscilloscope, right? Somebody reading your lab report has no idea why you drew a waveform. And there's no way they can reproduce your work and see if they got the same waveform. So as you're writing your lab report, keep in mind this idea that you want someone reading your report without access to this, right? They don't see the lab, they just see your report. Someone reading your report should be able to reproduce exactly what you did. So if you're asked to build a circuit and measure the voltage at the output, you can't just write the output voltage was 3 volts. What output voltage? Where did it come from? What was the circuit? You can't say we built the circuit and the output voltage was 3 volts because they don't know what the circuit was. You'd have to have a circuit diagram. And you'd have to say what output did you measure the voltage on? Okay? So think about lab reports from the point of view of if somebody who has never taken this course, never seen the assignment, all they have is your report, can they reproduce your work? That's the real goal of a lab report. Okay, and I'll give you a lot of feedback on the first report, and I won't take off many points, but I'll give you a lot of feedback along those lines. And we'll work towards, by the time we get to the end of the course, writing professional quality lab reports that really give you something that somebody else can use to reproduce your work. All right, cool. So I got office hours until 3 o'clock if you have anything you want to talk about. Otherwise, I will see you on Thursday.